Hello everyone, welcome to this video session on embedded Rust. I am Sandeep Saxena. In today's video, we are going to learn to blink LED using Rust programming language, and we will be using this STM32 F103 microcontroller, which is a Cortex M3 based 32-bit microcontroller from ST. And this series of lectures will be specifically designed for embedded Rust programming and understanding. So the question is, why Rust? So in Rust, we have this memory safety without garbage collection. Rust uses a strict ownership model with borrow checking at compile time to prevent common bugs like null pointer dereference, buffer overflows, and data races. So in this, it's like when we consider a case of C language, we take a variable int a is equals to 10, and let's say we took another variable that is int b is equals to a. So in that case, both a and b gets the value of as 10, but in case of Rust, it will give you an error saying that ownership of a is expired. So unlike C and C++, Rust enforces memory safety without needing a garbage collector, making it ideal for performance critical applications. So Rust is high performance. Rust is as fast as C, C++ because it compiles to native machine code with zero code abstractions. It allows fine-grained control over hardware resources, making it great for game engines, operating system, and embedded systems. So this language can be used as a system programming language as well as games, like we used to have C++, operating systems which is mostly written in C and C++, and of course embedded system that is mostly written into C. So this Rust is having fearless concurrency. Rust ownership model prevents data races at compile time, making concurrent programming safer and easier. It enables writing highly parallel programs without the risk of race conditions. So this we will be seeing later on when we will be dealing with the POSIX related stuff in Rust. So this series will basically meant for this embedded system STM32 based microcontrollers. Maybe we'll go for some Linux based stuff later on, but primary focus will be on microcontroller as of now. Cross-platform support. So Rust supports WebAssembly, enabling high-performance web applications. It works on embedded devices, servers, and even with browsers. Strong ecosystem and tooling. So Cargo, that is Rust's package manager that simplifies dependency management and builds. That this we will see in our this current lecture. And Rust FMT and Clippy ensures clean idiomatic code. A growing number of libraries, traits. So we will be understanding what traits are, and I'm assuming you have a little bit knowledge of Rust before seeing this lecture. Even though if you don't have an idea of Rust, you may get some idea from this lecture. This will be very basic, which I'm going to teach today. So as mentioned, like it can work with almost everything like system programming, OS, device drivers, game development, which used to happen in C++, even now it is happening, and web backends, embedded and IoT, cryptography and blockchain, and WebAssembly. So this is the Rust program we have written for this LED, which is connected on this board on PB2, that is port B pin number 2, and this is written for STM32 F1 family of microcontroller, and let me break it down for you. So first line says no STD. This indicates the program doesn't use the Rust standard library, which is common for embedded systems. No main means we are not using the standard main function as the entry point. So these are the crates which we are using in this program, in which first crate use panic halt as underscore. So this defines what happens when the program panics or crashes. Panic halt is a panic handler that simply halts the processor when panic occurs. The underscore syntax means we are not we are using it without giving a local name. So in embedded systems, you must explicitly define panic behavior, since there is no OS to handle crashes. As we have access to the memory, reading and writing to registers directly using our code, so we need something to handle such panic situations if we do some sort of null pointer dereference or something. Then there is Cortex M RT entry. Cortex M and RT stands for Cortex M runtime. So this attribute marks your main function as the program's entry point. As we know that we need some startup code for each and every processor, so this handles that startup code, initializing the microcontroller's RAM, setting up the stack pointer, initializing static variable. So this replaces standard main function in embedded context. So that's why it is needed. And then we have this Cortex M delay function, delay crate, that also we have imported here. So this provides the blocking delay functionality, uses the system timer peripheral to create accurate delays. So this provides some methods like delay ms, delay us, ms for millisecond, us for microsecond. And then last we have this pack and prelude. So pack stands for peripheral access crate. So this provides the peripheral which is the device specific peripherals. So there are two types of peripherals we use in our SOC. So that one is DP and one is CP. So CP stands for the core peripherals and DP stands for the device peripherals. So in device peripherals we have peripherals like GPIO, UART, etc. And in core peripherals we have peripherals like NVIC, system timer, like that. So this pack or peripheral access crate is generated from system view description file. So this provides the direct access to all microcontroller peripherals. And prelude, this imports commonly used traits and types like underscore embedded halt traits, extension traits for GPIO configuration, clock configuration utilities, digital IO traits. So common items to bring into scope is GPIO, like it will split the GPIO for you. Let's say if as I'm using here PB2, so as you can see I'm using this split function over here. So this will split this single pin and it will provide me this in this variable so that I can play with it. So next we have is entry, and function main tends to not. So this is the Rust based syntax actually, which says that this function never returns. So hash entry marks this as program's entry point, replacing the standard main. And like I said, this tends to operator not indicates that function never returns. And let me break it down, that line number 14, that is DP, which is device peripherals. So in this DP variable we are taking the peripherals from the pack crate. So purpose of using this or taking this like to access the microcontrollers device specific peripherals. So PAC stands for peripheral access grade. Peripherals, a struct containing all the microcontrollers peripherals like GPIO, UART, SPI, timers, etc. Take. This is a method that tries to take ownership of the peripherals and unwrap that asserts we successfully got the peripheral. And if we don't get the peripheral successfully, then this unwrap will panic if that peripheral is already taken. So what it will give to you, this will give you the full access to microcontroller peripherals like GPIO A, GPIO B, UART, timer, RCC, etc. So this will ensure the safe and exclusive access to hardware resources, and it will prevent multiple parts of the code from accidentally controlling the same peripheral. So again, then line number 15 we have CP. So that uses the Cortex M crate. So I will explain that. So the purpose of this to access the core peripherals from the processor core. So like I explained, we have an NVIC or system timer. So that again there is a struct containing the core peripherals. So again, take dot unwrap is for pattern for safe access. So what this will give us, it can give us the system timer, NVIC, memory protection unit, etc. So for DP, the importance of DP is chipset specific, and for CP it is Cortex M standard. So DP contains the peripherals and CP contains the core peripherals. Then we have this flash. So what will happen, we took from DP, we are trying to access flash, and we are using a method called constrain. So this converts it into a high level type safe interface. So again, same thing we are doing for RCC, which stands for register for clock control, and then we are using RCC CFGR register to configure the clock. So CFGR stands for clock configuration register, which can give me multiple options to set the clock. I can set HSI, HSE or PLL as my system clock. So this includes the configuration for different buses in the SOC, let's say AHB, APB. So all that configuration I can do from this register. And why this parameter flash ACR? So this grants access to flash memory's access control register to set wait states. Now we will see the GPIO setup. So as you can see, I have splitted this GPIO. You can see some commented code over here. So that I was using for a different microcontroller. It was same microcontroller but different board, which was having this LED on PC13, that is port C and pin number 13. So I was using this for that, and now I'm using this different board, which is again a blue pill, which comes with a newer version with type C interface. As you can see, here is a type C interface in this. So I found this LED here on PB2, so I commented that code and I made it as PB2. And from DP itself we are taking GPIO B, and then we are calling a method called split. So then again I have one variable called LED. From GPIO B we have PB2, and we are making it as push pull output. And as you can see, pin number 13 we are having CRH, and pin number 2 we are having CRL, because this the configuration register low and configuration register high. When we take pins from 0 to 7 we use CRL, and when we take pins from 8 to 15 we take it as CRH. And this is our main loop, so I'm calling this method from set high and set low to set my LED as high or low. And I'm using a delay of 200 milliseconds over here. That will help me see whether this delay is perfectly working fine or not. So first we will try to make it as 1000, and we will compile this code. So one thing that we missed out over here is cargo.tuml file. So this file contains the package details, that those are binary or library crate with the name of the project. So in this case STM32 Blink, and then we have this dependencies section which explains the crates from the core as well as SOC side. So this contains the crates from HAL as well as the core crates, that is Cortex M and Cortex M runtime, and NB stands for non-blocking IO abstractions. And then we have this panic halt. We have this linker script file which tells the origin as well as size of the RAM and ROM in this microcontroller. So we have 64 KB of flash and we have 20 KB of RAM, so the starting address of both. So this tells, and there is a lock file which is not created by us. When you use such crates and you import them in your code, then you see a log file which is created. So this is an automatically generated file by Cargo. So Cargo, as I explained, Cargo is the Rust package manager that records exact versions of dependencies used in your project. It ensures reproducible builds by locking dependency version, even if newer versions are released later. So this is automatically created and updated. So let's now compile this and we'll see what happens. So I will type, okay, I have written some steps over here. So when I say cargo build release, it will give me an ELF file. Okay, let's compile it. Okay, so it compiled successfully. So this command, I'm using OpenOCD as a programmer to program my STM32 here. You can use a different tool or you can use the same tool. So I'm telling from where you have to start flashing. So this I will explain a little bit later on. So yeah, now what we have to do, we have to use this tool called Rust obj copy to get this as the pin file, because currently we got, if you see this folder over here, we got this file in the target release, no, in this, yeah. So yeah, this we have as the ELF file, not as the pin file. So to make it, we have to use Rust obj copy, and we will try to make it as binary file. So after doing that, we should be able to see the binary .bin file over here. Okay, so I'm going to run this command. Okay, yeah, I have the bin file right now. So now I just need to flash it. So I'm using this same command and I'm going to flash it. Okay, so as you can see, it started blinking LED on PB2, that is the blue LED. So why we made this binary? That is the question, why we couldn't use ELF format. So there are some tools like probe RS that can flash ELF files, but OpenOCD or ST flash that expects the raw binaries. So let us try to understand this command first. So as you can see, this was our input file and this was our output file. So this we got as our raw binary, and let's try to understand this command now. So as you can see, OpenOCD -f interface stlink.cfg that specifies the debug probe, and then we have -f target slash STM32 f1.cfg that specifies the target MCU. Then we have -c, then program command, and then verify, program with this binary, then verify, then reset, and then exit. So this is how this works in Rust. Currently I don't know whether any IDE or full-fledged IDE is available for Rust. If you guys know, please let me know. So thank you guys, thank you for watching.